Hello, my name is Michelle Gaynor, President of the University of Michigan Mars Rover team, and welcome to our 2020 System Acceptance Review. Our team has been hard at work redesigning our rover systems to increase its capabilities in each mission. In this video, we will showcase features that will strengthen our performance at the University Rover Challenge.
This year's rover was developed with a focus on durability and reliability. A carbon fiber chassis provides a strong, lightweight foundation. High stress points are reinforced with structural inserts, and a modular design facilitates smooth configuration changes between missions. The mobility system has been revamped with more powerful and brushless DC wheel motors, which will help the rover climb steeper slopes in the extreme retrieval and delivery mission. The suspension is optimized for driving forward to better absorb frontal impacts. Additionally, the wheels are 3D printed from flexible polymer to enhance the rover's compliance and traction when traversing desert terrain. This year's 6 Degree of Freedom robotic arm features in-house cycloidal transmissions, which increase end effector precision and reduce overall mass. The linear actuator on the shoulder pitch joint ensures that the robotic arm is strong enough to tow and lift a 5-kilogram payload with the rope. A 2 Degree of Freedom gimbal camera provides an adjustable view during robotic arm operation. To test the rover for the extreme retrieval and delivery mission, we have designed multiple courses which include terrain and objects similar to what we expect to see at competition.
We have automated the operation of the robotic arm to officially complete competition objectives in the equipment servicing mission. Our inverse kinematics-based control scheme now includes an orientation mode, allowing the operator to command the end effector's orientation and location of the robotic arm. Using our kinematic model, we calculate a torque feed-forward term to augment our existing high-frequency feedback controller, thereby ensuring smooth operation of the arm. Our end effector uses a lead screw to grip objects up to 3.5 inches wide with strength and precision. Intersecting lasers guide the operator to line up a hex key for tightening a screw and typing on a keyboard. Rover operators will practice controlling the arm using open loop and motion planning algorithms on a configurable lander.
For the redesigned autonomous navigation mission, we've upgraded our navigation, localization, and computer vision software. The rover makes safe and strategic path planning decisions to traverse GPS waypoints using odometry and computer vision data. Localization is performed using GPS sensors and a 9-axis IMU. This year we developed Kalman and Madrick filters to increase the precision and reliability of this data. We also augmented our navigation state machine to include gate detection and computer vision assisted gate traversal. A stereoscopic camera is used to identify the IDs and distances of AR tags relative to the rover so that the state machine can determine the directionality and center of the gate. The rover aligns itself precisely between the two posts and passes through the gate in the correct direction. The computer vision software also detects potential obstacles as small as 20 centimeters up to 5 meters away. When the rover detects an obstacle, a safe alternative route to the next waypoint is identified and executed. We have developed test courses that imitate this mission as well as an idealized simulator to test our navigation algorithms year-round.
To support our rover's mechanical and software updates, we have completely overhauled its electrical system. We built a 10 series lithium-ion battery pack using 18650 cells to provide 36 volts to the rover. Additionally, we incorporated brushless DC motor drivers which enable precise control of the wheels. For reliable communication, the rover is equipped with a 900 MHz radio and linearly polarized antennas. The radio communicates with a 3-meter base station antenna from up to 1 kilometer away. We also built an autonomously deployable radio repeater for long-range missions. The repeater is made up of 4 patch antennas mounted on a tetrahedral structure. The device is deployed by a burn wire release mechanism to ensure constant omnidirectional communication after deployment.
We've designed a suite of scientific instrumentation to analyze both soil and rock samples for evidence of life. A 3 Degree of Freedom sampling system collects soil with sterilized interchangeable end effectors, which are replaced in between sites to prevent cross-contamination. Each sample is deposited into one of 4 isolated enclosures, including 3 identical suites of chemical tests and 1 Raman spectrometer. The chemical tests are equipped to detect biomolecules, including photosynthetic chlorophyll using a spectral sensor, ammonia using color indicator strips, and amino acids using ninhydrin solution. The results of all chemical tests are streamed back to the base station for immediate evaluation. The second iteration of our custom-built 650 nanometer Raman spectrometer is designed to detect kerogen and carotenoids in a sample. A microscope and reflectance spectrometer are permanently mounted to the end effector to analyze rock samples in situ. The microscope images sites that may contain gross morphologies indicative of fossilized or living microbial communities, while the reflectance spectrometer searches for mineral evidence of life such as limestone or diatomaceous earth. The sample acquisition and analysis process will be tested on a course with marked soil and rock samples from southern Utah.
Our efforts in the final months before competition will emphasize full system verification and operator practice. We will conduct a series of mock missions under the same constraints that we expect at competition. Our performance in these missions, as well as past competitions, will be used to develop competition strategy. We are confident in our ability to succeed at the University Rover Challenge. On behalf of the Michigan Mars Rover team, thank you for your consideration, and go Blue!